Here are solutions to homework set number 15 for ECE 111, Introduction to ECE. This homework set looks at using Matlab to solve the problem where I have a transfer function or differential equation where the input is not a sine wave. Specifically, what if I have a triangle wave like this? So here essentially is the problem. This is Circuit Lab. If you scroll down in Circuit Lab, here's a feature that was just added recently. There is a transfer function block, this guy. What that lets you do is you can input your filter. In this case, we have 0.5 over s squared plus s plus 0.5. Pretty much the way you type it. If the input is a sine wave, well, that's what we did last week. If you have a sine wave as an input, the output is a sine wave. So here's your input, there's the output. I can solve that using phasors. Here the output is gain times input. The input is your sine wave. The gain is 0.5 over s squared plus s plus 0.5, where s is j omega, and omega is 2 pi f. In this case, omega is 1, frequency is 1. Well, what happens if the input is not a sine wave? For example, suppose the input is a triangle wave. In that case, here's the input, a triangle wave. You get an output. How do I express that mathematically? Suppose the input is something else that's periodic, but not a sine wave. I could have a sawtooth wave. And here's the input, the blue line, the sawtooth wave. There's the output. It's no longer a sine wave. How do I calculate that? Or finally, if I go down here, I could have a square wave input. There's the input, a square wave. There's the output. Again, it's not a sine wave. How do I find the output when the input is not a sine wave? Well, this goes back to my favorite joke about a fire extinguisher and trash can. Once I come up with a solution, if I can force the problem to fit that solution, I can solve different problems. So we have a solution. Find the output when the input is a sine wave. If the input is not a sine wave, change the problem. Change this into a sine wave. That's what this problem is all about. This homework set's all about. That's called Fourier Transforms. It's one of the more confusing topics when you get to signals, but it's really not all that bad. It's just curve fitting. So the first problem is you can curve fit anything. Suppose I have my triangle wave and I want to represent it as a power series. Well, I can do that with least squares. What I would do is input time. Your time goes from 0 to 2 pi. Offset a little bit just to avoid 0. That's an issue. My triangle wave is t between 0 and 2, 4 minus t for t between 2 and 4, and then 0. So input x into Matlab. My basis function is just 1 t, t squared, t cubed, t to the 4th, t to the 5th. So there's my basis. Then the least squares curve fit is what we've done before. Inverse of b transpose b, b transpose times x. So these are the weightings. That's the weighting times 1 times t squared, t cubed, t to the 4th, t to the 5th. And I can see how that looks. If I plot t versus x in blue, t versus my curve fit, that's the basis times these constants in red. This is x, there's my curve fit. Yeah, not perfect. If I add more and more terms, I get a better and better curve fit. That's just curve fitting. This is a power series expansion. In terms of filters, it doesn't really help because I have my filter, h of s. I've got my input x. If x was a sine wave, I would know what to do. Well, x is not a sine wave. I express it as 1 t, t squared, t cubed, and so I still don't really know what the output is. Let's try a different basis. Suppose I pick the basis to be 1 cosine of t, sine of t, cosine 2t, sine of 2t, and so on. Again, your function is periodic in 2 pi. These are sine waves that are also periodic in 2 pi. Pick a basis. Now let's do a least squares curve fit. So again, here's t, x, just like before. Now we'll make the basis 1 t, cosine t, sine t, cosine 2t, sine 2t, cosine 3t, sine 3t, least squares curve fit. I get numbers. If I plot the data versus the curve fit, it matches reasonably well. Again, that's surprising, it's just a curve fit. What's significant, though, is now this basis, or this curve fit, is useful. I have my input in terms of sine waves. I've got my DC term, the first harmonic, 1 radian per second, second harmonic at 2 radians per second, third harmonic at 3 radians per second. I like sine waves. I know what to do with sine waves. So now I can do what we did last week using phasors and superposition. Analyze. Find the output at DC, at 1 radian per second, at 2 radians per second, 3 radians per second. Add them all up, I'll get y of t. That's really all Fourier transform is. It's pick a basis that's useful. Pick a basis that's made up of sine waves. Do a least squares curve fit. Once I have x in terms of sine waves, I know what to do with it. I like sine waves. So that's one way to find a Fourier transform, least squares. There's another way to do it. Another way is if I have x of t, let's go back over here. In terms of all these sine waves, I can find the terms one by one. For example, to find a0, I just take what is the average of x. Well, the average of sines and cosines are 0, so this term is 0, that's 0, this is 0. All these are 0, so just finding the average of x gives me a0. Suppose I want to find a1. Well, if I take x of t and hit it with cosine of t, then take the average. Well, the average of cosine is 0. Average of sine times cosine is 0. Average of cosine times cosine of 2t is 0. 0, 0, 0. Everything's 0 except this term. The average of cosine squared is a half. So I can find a1. a1 is just 2. That clears out the half. Times the average, or Matlab speak, the mean of x hit with cosine of t. And likewise for b1, c1, and so on. So that's another way to do it. If I do that and say what is the average of x, that's a0. Same as we got with least squares. What is twice the average of x hit with cosine of t? That was a1. Same answer as before. Twice the average of x with sine of t, that's b1. So this is just another way to find the coefficients. The reason this works is sines and cosines is an orthogonal basis, so I can find each term independently. That's what orthogonal does for you. It's not orthonormal. Orthonormal would be all these weightings are 1. They're not 1, it's not orthonormal, just orthogonal. That's just another way to find the basis elements, or to find the Fourier coefficients. And in Matlab I can do that. Here I'll just input x, find the basis elements, and then just let's add them up one at a time. So here's the DC term, first harmonic, second, third harmonic. Or, let's put that in for loop, I can go out to 7 harmonics. There's the DC term, first harmonic, second, third, fourth, fifth, sixth, seventh. As I add more and more harmonics, it gets closer and closer. And let's go out to 28 harmonics. DC, first, second, third, fourth. That's what the Fourier series does. As I go out to infinity, I get closer and closer. In theory, I have to go to infinity. In practice, if you just include a couple terms, you're usually close enough. To be exact, I have to go out to infinity. Infinity is a hard number to work with. Practice, engineers say, once I'm close enough, good enough, I'll just go out to a couple terms. So that's the input. Once I have the input, I can now find the output. Now this uses superposition. What superposition says is if I have a function f of a plus b plus c that's equal to f of a plus f of b plus f of c, that's what linearity means. Superposition says if I have a linear system, I can treat this problem, where I have a bunch of sine waves added together to produce x, that's this waveform. Treat that as separate problems. I've got the first harmonic at DC. X is just 0.63. Find the output at that frequency. At 1 radian per second, here's the input. find the output at that frequency. Likewise at 2, likewise at 3. In Matlab, the way you do that is at DC, s equals 0. My input at DC was x0, 0.6365. The output is gain times input, 0.6365. So there's the DC term. Let's go on to 1 radian per second. At 1 radian per second, s equals j. X is what we calculated before. At the first harmonic, the cosine term and the sine term. In phasors, the way you represent that, the real part's cosine minus j is sine. That's where that minus sign comes from. Output is gain times input. Here's the gain. I calculate the gain at 1 radian per second times the input at 1 radian per second. There's x. I get the output 1 radian per second. Real part's cosine minus j is sine. At 2 radians per second, s is j2. This is what the input was at 2 radians per second. 0.17 cosine minus 0.19 sine. Output is gain times input. So here's the gain at 2 radians per second times the input, gives a complex number. Real part's cosine minus j is sine. Likewise at 3 radians per second, and so on and so on. Here's the input, here's the gain, here's the output. The total answer then is the sum of all those parts. Add them all up, I get y of t. And I can see that in Matlab. Here's what it looks like. For Matlab I can do that. I first find x in terms of sines and cosines. Find the DC term for y, the first harmonic for y, second harmonic, third harmonic. Add them all up, I get the waveform for y. So this is doing it bit by bit. So this is the DC term plus first harmonic, second, third. Or going on, if I go out to, let's say, 28 harmonics. I'm going to put this in matrix form. Find the sine and cosine term after 28 harmonics. You don't have to, but I'm just doing that to show off. Add each harmonic. I know the input. Here's the gain at that frequency. Output is gain times input. The real part's cosine minus j is sine. What that looks like is this. So there's the DC term, first harmonic, second, third, fourth, fifth, sixth, seventh, eighth, all the way up to 28. If I go out to infinity, I get the waveform. If you kind of notice, it's not really changing. That's the saving grace of Fourier transforms. In theory, you have to go out to infinity. In practice, if I just include a couple terms, I pretty much capture the waveform. And you can see that in these solutions. This is the term going out to the third harmonic. This third term is so small, if I ignore it, I'm not that far off. I'm only up by 0.00012. So if I just include 3 terms, I'm pretty close. The second harmonic, it's there, but it's really small. So maybe 3%. If I want to be accurate to less than 3%, I need it. If 3% error isn't bad, I can throw that one out. I'm going to see what the output looks like. Here's the output that looks like a sine wave. So if we just include the DC term, that's the offset, and the first harmonic, that's this guy, I pretty much have the output. It's not exactly a sine wave. There are harmonics. There's the second harmonic, third harmonic, fourth harmonic, and so on. They're pretty small though. So in theory I have to go out to infinity. In practice, a couple of harmonics are usually good enough. The power of this is any input that's periodic I can now handle. The trick is if my input is periodic but not a sine wave, turn it into a sine wave. That's what we were doing here. I have a waveform that's not a sine wave, start adding up more and more terms, and I get a better and better approximation. Once I have sine waves, I can now analyze it. With sine waves, I use phasor analysis. At any given frequency, I know the frequency, I know the gain at that frequency, I know the input at that frequency, output is gain times input. Add them all up, I get the total output. kind of like so. This is the DC term, first harmonic, second, third, fourth, fifth, sixth, seventh. Pretty much past the second harmonic doesn't really matter. And with this, I can now find the output of a differential equation or transfer function for any periodic input. That's the power of Fourier transforms. Once you have phasors, once you have superposition, you really have Fourier transforms. And that is homework set number 15 for ECE 111.